lecture was very enjoyable, right? No? Okay. I will begin. Heavenly Father, we thank you for this day. Again, Lord, I thank you for these students. I pray you help us use this time wisely, Lord, for your glory. In your name I pray, Lord Jesus. Amen. I think the best thing I could do right off the bat is just give you an example of the Jordan form, because that's the one thing that's kind of missing last time. And then after that, I'll take your questions. So let's look at the matrix A equal to, and I don't know if I, do you guys have, if maybe some of you have read the notes more carefully than I have recently, did I introduce a notation for the real Jordan form in the notes? Like, oh, I don't have them with me. So what I'm saying is, did I at some point introduce a notation for like this one? Do I have some notation for that? Like, no? That's annoying. Let's see here. What should we call it? How about this? This would be the real Jordan form of 2 plus 3i, something like that. Or maybe, I don't know. You know, let me do real Jordan of that. So suppose you have the real Jordan form of 2 plus 3i, and this is just, and then the real Jordan form, a 2 by, you know, the repeated case of 7 minus 4i, and then let's say you've got a 3 by 3 regular Jordan block for eigenvalue 7. Well, no, let's say 8. I haven't used that yet. And then you've got a 1 block for 9 and a 2 block for 10. So what I want to do is just look at what this matrix looks like and describe what the standard basis vectors are for this matrix, what they mean to this matrix, all right? So already, this matrix is in real Jordan form because it's a direct sum of real Jordan form blocks. So like the stupidest case of real Jordan form, well, I don't know if it's the stupidest case, but a case of real Jordan form is just the ordinary plain Jane Jordan form of a real eigenvalue. All right, so the last bit of it's just ordinary eigenvalues. So what's this look like? I guess I need to, this is huge, isn't it? How big is this? This is a 2 by 2, right? This piece right here is actually 4 by 4, right? This piece right here is 3 by 3. This piece right here is 1 by 1. And this piece is 2 by 2. So how big is the matrix we're looking at here? The 12 by 12, right? So let's see here. I'll get us started. This is, the first block is 2, 3, minus 3, 2. All right. And then the next 4 by 4 block we have here would be 2, 3, minus 3. Oh, I'm sorry, I can't. I did 7 plus 4i, didn't I? Minus 4i, rather. So this would be 7 minus 4, 4, 7, 7 minus 4, 4, 7. And this is essentially by the calculation we did towards the end of class. I mean, that's why that has this particular pattern. Okay, so that's the first two. And then a 3 by 3 8 block, that's 8, 8, 8. One's on the superdiagonal. A 1 by 1 9 block, here it is. And let's see here, a 2 by 2, 10, 10, 1, 0. Right, and it's 0 elsewhere, okay? outside of these blocks is 0. It's a block diagonal matrix. So here's the thing. Here's a thing that will probably help you with any number of homework questions I've asked you in either direction, but here's the point. If matrix is in real Jordan form, then standard basis, E1, E2, etc., form either eigenvectors, generalized eigenvectors, components rather, of complex eigenvectors, or components of generalized complex eigenvectors. So a lot of pure math types just skip this topic because they don't like it. It's kind of cluttered. You know, it's much cleaner and neater just to talk about the Jordan form, right? And then if you want to talk about something that holds for arbitrary fields, you talk about something called the rational canonical form. The beginning of the discussion, which leads to the so-called rational canonical form, is in that section I skip that I mentioned at the end of class. But the reason I talk about the real Jordan form is because, you know, a lot of you are more or less applied mathematicians. You're going to go work perhaps possibly for industry, possibly for, whatever reason. And so often the problems we encounter are real problems, right? They're systems of real variables, and so you're interested in real solutions. And it is not the case that any real matrix can be put in the Jordan form, because you might not have enough eigenvectors, like eigenvalues, right? You have complex eigenvalues. But it is the case that any matrix can be similarity transformed into real Jordan form, because you can always find a complete set of eigenvalues in the complexification of the matrix. From there, you can find a complex basis, and from that, you can extract the corresponding real Jordan basis. So these things together form what I would call the real Jordan basis, which again, technically speaking, is not a Jordan basis because it's not just made of eigenvectors. It's made of these kind of hybrid things that involve the interface between the complexification and the matrix. Okay, that's the big picture. This specific matrix, can you tell me what are my set of eigenvectors? Maybe I should write it over here, actually, on the other side. Work myself into a corner. So if you look at it, this guy, this one, and this one, if you think about multiplying this matrix, right? If you multiply this matrix, let me finish the story here. Zeros, 0, 0. Wait a minute. 0, 0. Can't count. 0, 0, 0, 0. What's down here? 3 zeros, right? And this 9, you know what? So what happens if we multiply the matrix by which column is, if you multiply the matrix by the standard basis corresponding to this column, it just selects that column, right? So you can see from my purple zeros that A times E what? E7 is equal to what? It's equal to 8 E7, right? And you can see that 9 E10, is it? A times E10 rather is 9 E10, and A times E11 is 10 E11. So my eigenvectors for this matrix are just those ones, E7, E10, and E11, right? How about generalized eigenvectors? Where are generalized eigenvectors coming from? they're coming from this block and that block, right? So from this right here, I can get that A times E8 is equal to 8E8 plus E7 from this one right here. And from that, I can get that A E9 is equal to 8E9 plus E8, which is to say that A minus 8I times E8 is equal to E7, and A minus 8I times E9 is equal to E8. And then, of course, we already noticed that A minus 8I times E7 is equal to 0. So this is basically a 3-chain for lambda equal to 8. And, so E7 is the eigenvector, E8 is the generalized eigenvector order 2, and E9 is the generalized eigenvector order 3, all for eigenvalue 8. That's that 3 by 3 block.
So that whole right side there is your generalized eigenvector form?
This piece?
No, the A minus 8I E7, that whole...
This is the chain condition. These are the chain conditions that I call these I sometimes call these chain conditions because they tell you the interrelation of the generalized eigenvectors corresponding to eigenvalue 8. If we could say this, Emily, so like K, the generalized eigenspace for K, the generalized eigenspace for lambda equal to 8 would be the span of E7, E8, E9. I don't think I even give a name for the corresponding kind of space for these pieces in this case, though. So, not that I recall anyway, but it's been a little bit since I typed these notes. Okay, and then finally, what's the 10 by 10 block? The 2 by 2 10 block gives us what? If you look at that, we've got, AE11 equal to 10E11 plus E12, right? So that's A minus 10I. So if you look at it, it's A minus 10I times E11 equals to E12. And of course, we already have that A minus, oh, I'm sorry, I can't do math. Did I say, what should I write here? This is backwards, right? It's the 12th one. I should say AE12 equals to 10E12 plus E11, right? If you look at this last column, it's 1 copy of E11 plus 10 copies of E12. So that's why I have A times E12, that's the 12th column, is 10 times E12 plus E11, which translates into A minus 10I times E11, good grief, E12 equals to E11. And this dotted equation right here already told us that A minus 10I times E11 is equal to 0, so you look at these two conditions together. This is the chain condition, these are the chain equations, if you like, chain conditions for lambda equals to 10. It's a 2-chain. For what it's worth, the generalized eigenspace for lambda equals to 10 would be the span of E11 and E12. All right, so far I've just focused on the actual real eigenvalues and the corresponding generalized real eigenvectors. Now let's go on to the complex stuff in here. So the 2 by 2 block here, right? I guess I need yet another color. It's going to get really busy. But this piece right here, right? What that tells me, right, is that A times 2E1 plus, I'm an idiot. A times E1 plus IE2 is equal to 2 plus 3I times E1 plus IE2. I better write in a color that actually we can see. Sorry about that. Yeah. Maybe this one will work. Yeah, there we go. So what I'm doing right now, guys, is I'm just working backwards from what we did last class. All right? That's all. I showed you that if we had a complex eigenvector, for the complexification, then if we look at the basis corresponding to that eigenvector, its real and imaginary parts, then the matrix has this form. So I'm just saying that process can be reversed. If you think about, I have in mind in this reversal, what's the transformation I'm thinking about? I'm thinking about t is equal to left multiplication by a, right? Which is naturally a mapping, in this case, from R12 to R12, right? And then the complexification of t would be a mapping from where? From C12 to C12. And it's that complexified t which actually takes E1 plus IE2 as its complex eigenvector with complex eigenvalue 2 plus 3i. So that's the one thing. So we have, complex, this is a complex eigenvector with complex eigenvalue lambda. And then finally, we also have that a times E3 plus IE4 is equal to 7 minus 4i times E3 plus IE4. And also we have that a times E5 plus IE6 is equal to 7 minus 4i times E5 plus IE6 plus E3 plus IE4. That's coming from this right here. And again, the thing I did in the last about 15 minutes of class, I'm doing backwards here to get that. So I think if you really understand the example I just did, you can do probably 80% of the homework I've assigned. Because most of the homework I've assigned is really just interpreting the relation between the Jordan form and the standard basis and or vectors which are given, right? I mean, we could have a transformation and I can give you formulas and you can interpret them, right? Go play that game for a minute. Let's try. Suppose I have V1, V2, V3, and I tell you that T of V1 equals to V3, and I tell you that T of V3 equals to 0, and I tell you that T of V2 is equal to, 10 V2. And I say, okay, find me a Jordan basis for T. So how would you do it? See, this is a decent test question because I could ask this and I could pretty much ascertain whether or not you understood what was going on without burdening you with 2 pages of calculation. Right? Because if you've understood our definitions, you should be able to look at this and tell me 2 things really easily. Can you guys tell me? Let me ask a more probing question. What's V3? What's V2? These are eigenvectors, right? So we have t, if you look at it, t minus 0, right, times V3 equals to 0. In other words, V3 has lambda equals to 0, right? And it's just straight an eigenvector. Now, in fairness to you guys, until I tell you that v1, v2, and v3 are non-zero, we can't. If these are 0, then it's no help. All right. But it is okay. And then also, how about t minus 10? T minus 10 acting on v2 gives us what? Anyway, so this should also make it clear that v2 is an eigenvector, right? Lambda equal to what? 10, let's say. So let's call the first one 1, and let's say that the eigenvalue lambda 2 is 10. Let's say lambda 1 is 0. So what about the first condition? What does that tell you? But what is it?
It's equal to v3.
Yeah, that's given. Here, let me rewrite it. We could also write this as t minus 0 times v1, acting on v1, equals to v3, right? So what happens if you hit it with another copy of t minus 0? What's t minus 0 v3, though? It's 0, right? So what does this make v1? Generalized, right? Eigenvector with eigenvalue lambda 1 equal to 0. Is t diagonalizable? What does it mean for a transformation to be diagonalizable? It means that there exists a basis in which the matrix is diagonal. So is this transformation diagonalizable? Well, what's the matrix of t in this basis that we're looking at? So if we let beta equal to v1, v2, v3, then t beta beta is what? Oh, first of all, I shouldn't do that. Why shouldn't I do that? What goes together? We're supposed to put the eigenvector first, then the generalized eigenvector second to make the 2 chain for lambda equal to 0. So 2 is out of order, and v3 is supposed to come first. So the basis I should do, it shouldn't be this. We should do like v3, v1, and then v2 perhaps. All right. Because v3 is an eigen. You always want to put the eigenvectors first in the list, then generalized eigenvector order 2 next, and so forth. Work up the chain. The last thing in a given corresponding to a given block should be the highest order eigenvector that you have, generalized eigenvector. So if I do that, then the matrix looks like what? It looks like v3 is 0. So I get 0. We get 1. v2 had eigenvalue, wow, 10, yeah. And of course, this is j2, 0, direct sum j1, 10. There's one other correct answer that could be given here. What would it be? I could use gamma. What's the other basis I could choose that would also be a Jordan basis? No, I didn't even tell you what. I have not told you what v1, v2, and v3 are. For all we know, v1 is equal to x squared plus xyz. v2 might be x xy, and v3 might be z to the 17th, and our v is the span of these trinomials. I mean, we just don't know what the actual form of the vector space is here, so. Yes, we could exactly reorder v2, and then v3, and then v1. And so the heavy-handed point I'm making is that the Jordan form it's not unique exactly, but it's almost unique. It's unique up to what? Up to the ordering of the blocks. See, so this is J110, direct sum J2, 0. And so it's just a reshuffling of the blocks. So how many different Jordan forms are possible for a given matrix is kind of a pesky combinatorial question. So we don't really enjoy that question. So we just, our usual way of thinking is that two matrices are equivalent if they have the same Jordan form up to a reshuffling of the blocks. So I would say that the purple one and the red one are actually the same Jordan form. And what I mean by that more particularly is two matrices are equivalent if, I really should say that they're similar matrices because there's a similarity transformation to go from one to the other. Right, this is a theorem. If you want to know whether two matrices are similar or not, if they have the same real Jordan form, then they're similar. If they don't, they're not. See, I couldn't just tell you if two real matrices have the same Jordan form, they're similar. That wouldn't even make sense because a given real matrix, for example, this one, this matrix, right, has eigenvalues cosine theta plus I sine theta, right? So unless sine theta is 0, the eigenvalues are complex, and yet that's a very real matrix. Those are rotations in the plane. That's not a terribly exotic idea, and yet complex eigenvalues, right? So to answer whether or not that's similar to another matrix, I could look at the real Jordan form, and if the real Jordan form of both of the matrices was the same up to a reordering of the blocks, then they're similar. That's a theorem we have. I mean, you have other things you can test to see if matrices are similar, right? If matrices are similar, that means that B is equal to P inverse AP, right? So like what else what are kind of like no-go theorems? You can check determinant, right? Is the determinant of similar matrices the same? I mean, you can. So these cancel, and you just get. So like the determinant of similar matrices is the same. The trace of similar matrices is the same, right? But unfortunately, guys, that's not enough. I mean, there are dissimilar matrices that have the same trace and determinant. So it's not a smoking gun. I mean, like if you find that they have the same determinant and have the same trace, it doesn't prove that they're similar. But if they're not equal, it does prove they're dissimilar. So proving things are not similar is much easier than proving things are similar. What's a very greedy algorithm to check whether two matrices are similar? Find their real Jordan forms. If they're the same up to reordering the blocks, they're similar. Anyway, I shut up. So you guys must have questions, I think. Let me get out my computer. Huh. That was not smart. I left my water bottle in my computer bag since yesterday. It's not leaked or anything. It's just now I've got no water today. I blame the children. Not my own children, though. The children at church made me tired yesterday. Like, do you have verses to say? Yes. All right, open up the book, find the verse. She's gone. She's just gone like the wind. Like, a whole table away playing with her ponies. Emma, the verses. Okay, I look down to find the verse again. Look up. She's already back to the ponies. Emma, the verses. Kids. And that's, many of you have a distinct advantage over me. You have female voices. Female voices in a room of crowded children, you've got a chance of piercing through the noise so that they hear you. My voice, it just blends into the background in this context. It's horrible. Yeah, it's Awana. We do Cubbies too, which is, it's the bigger Cubbies. I like that age group. I like 4 to 5 year olds. They're fun. Mostly potty trained. No, I do not want to update my computer. Oh my goodness. I hate you, Windows. I hate you with a perfect hatred. Well, anyway, you can describe your problems with words. We'll look at them in a minute, or 5, or who knows. An indeterminate amount of time is set forth by the evil Microsoft Corporation. Let's see here. Oh, thank you.
Oh, that's only one.
Yeah, it's fine. Oh. Oh, man, this is long. Oh, wow. Okay. Yes?
I have a question about what's in this word.
Perfect. All right. That's good. That's fine. That's fine. We're still updating anyway. So go on.
I was just confused about the part that starts in red. How you know
In the what?
that that's a generalized eigenvector and what exactly that means.
So again, right, with this right here. So we defined a generalized eigenvector to be something of the form. So generically speaking, a generalized eigenvector, remember, I said a generalized eigenvector, order p, for eigenvalue lambda for a or t. I mean, the same pattern, right? But it has a minus lambda I to the p power, all right? Let's call that eigenvector v. V equal to 0, but a minus lambda I p minus 1 acting on v not equal to 0. And then with the and we also have a special case. When we have p equals to 1, then if we have a minus lambda I times v equal to 0, we just say it's a generalized eigenvector of order 1, and it's just a regular, plain old eigenvector. All right, so when p equals 1, it's a special case. Yeah? So this is, this is the definition of generalized eigenvector, but there's another thing we've noticed, which is that if we have a chain, right, if we have a minus lambda I on vj equal to vj minus 1, for j equals to 1, 2, p, then that will force vp to be a generalized eigenvector of order p. It will force vp minus 1 to be a generalized eigenvector of order p minus 1, and so forth. This stack of chain conditions will so let's look at p equals 2. So p equals 2, we've got a minus lambda I v2 equal to v1, right? We've got a minus lambda I v1 equal to 0. So if you hit the top equation with a minus lambda I, we get a minus lambda I squared. v2 is equal to a minus lambda I v1, which is 0. And yet, a minus lambda I v2 is just one copy of a minus lambda I acting on v2 gives us v1, which is by assumption non-zero. So that makes v2, in this context, a generalized eigenvector of order 2. So like the definition, again, I'm looking for the pth power of a minus lambda I killing the vector. So the vector's got to be in the null space of A minus lambda I to the pth power. That's what it means to be a generalized eigenvector of order P, paired with the condition that it's not in the null space of the P minus 1th power of this matrix. Pragmatically speaking, I obtain such vectors by this stack of chain conditions, because it's just a nice way to do it. So like here, we had the chain condition for V1 and V3. That's what this is. See, I had t minus 0 V1 is V3, right? But we had t minus 0 of V3 was 0. So V3 is an eigenvector, whereas V1 is a generalized eigenvector, order 2 for the eigenvalue 0. So that's why I put those in the Jordan basis. I'm not sure I've answered your question, though. Because you might have been asking a question from a different, perspective.
I think it does answer it.
Okay, so because sometimes students ask me, how to sweep the kitchen floor, and I tell you how to make the broom or something, So it's, yeah.
So in this case, V2 is the generalized eigenvector with e-value lambda.
Right. Up here, V3 is the eigenvector with eigenvalue 0, and V1 is the generalized eigenvector with eigenvalue 0, order 2. See, t minus 0 on V1 is not 0, it's V3.
So the thing at the very bottom of the chain is just the regular.
Right. Yes, the start of the chain is an eigenvector. The next thing up the chain is order 2. The next thing up for the chain is order 3, and so forth. Like here, if we had 13, 13, 13, 13, like this. In other words, we looked at the very unlucky, see here, very unlucky eigen 4 by 4 eigen 4 by 4 Jordan block with eigenvalue 13. This would give you 4 chain E1, E2, E3, E4. And actually, to move up this chain, what you could do, to get from here to here, you just multiply by A minus 13I. To get from here to here, you multiply by A minus 13I. To get from there to there, you multiply by A minus 13I. And what happens when you multiply E1 by A minus 13I? Well, E1's an eigenvector, so A minus 13I times E1 just gives you 0. But yeah, the standard basis here, E1, E2, E3, E4 is the Jordan basis for this matrix here, J4, 13. Since we're having this discussion, I should tell you guys something. Something I haven't told the class yet, and I don't know if I have or not, but it's something I should have mentioned. It's a shame for me not to have mentioned this yet. There's something called the Cayley-Hamilton theorem. Did I tell you guys this before? Cayley-Hamilton theorem. What it says, something pretty interesting, it says that if we have P sub A of x is equal to the determinant of, x, well, A, for us, I guess it's A minus xi, right? In other words, that's the characteristic polynomial, right? You guys have been working on it. We look for zeros of that. Those are our eigenvalues, right? Well, here's what Cayley-Hamilton theorem says. PA of A is equal to 0. Now, this, of course, is an nth order polynomial, right? It's like minus 1 to the n, x to the n, plus da-da-da, plus, some constant, c1x, plus c0, right? It's an nth order polynomial. There's some coefficients which define it. So when I say that PA of A is 0, what I'm saying is that this particular linear combination of the matrix, minus 1 to the n, a to the n, plus da-da-da, plus, c1a, plus c0 times identity matrix, that this is equal to 0. That's what the Cayley-Hamilton theorem says. Cayley-Hamilton theorem says that if you plug a matrix into its characteristic polynomial, it satisfies it, which is pretty neat, really. There's also something called the minimal polynomial. The minimal polynomial is like the smallest polynomial that when you plug the matrix into it, you get 0. And you can actually see the minimal polynomial from looking at these Jordan blocks, but I might have a homework about that somewhere. I don't know. I can't remember. But. All right, so you guys have other questions before I? Because this, what I'm starting to talk about, could easily eat up 20 minutes. I'm sure my version of Windows will be so vastly improved now that it has updated without my permission yet again. Is it too much to ask? I want to live life dangerously. I want to live with unupdated Windows, replete with all of its security risks. This is a risk I'm willing to take. Because the risk of a system update wasting my time is far more real. Let's see here. Let's face it, hackers really aren't going to find anything terribly interesting on my computer. Look, more math. What's that? They want to learn linear algebra. You guys are funny. Mission 6, mission 7, where are we? 7. All right. I'll find it here eventually. Come on. Open. Can I? Oh, you're still thinking. Still thinking.
Is V1 and V2 the generalized eigenvector?
Well, I would say that a eigenvector is a generalized eigenvector. It's the special case of a generalized eigenvector.
Okay.
So really only V2 is a genuinely generalized eigenvector. If you, I mean, it's just a question of language. Do you want to say eigenvectors are generalized eigenvectors or not? I think you could go either way. I mean, from a pure mathological perspective, they could be. It depends on the finer points of our definition, right? Usually when we define some sort of generalized thing, we have the tendency to allow the thing we're generalizing to be a special case of it, right? So to not do that here would be a little bit of a what's the word? We'd be avoiding the usual pattern, you know. But I know what you mean. I mean, I also think that V2 is the real generalized eigenvector and V1 is the eigenvector. Wait a minute, which are we talking about? I've got like 5 examples on here. Here, the one at the bottom. The one in the bottom in brown, V2 is the generalized eigenvector, V1 is the eigenvector. Yeah. What I cannot say is I cannot say that V2 is an eigenvector, right, with eigenvalue lambda, because A minus lambda I, and V2 is not 0. We good? Okay. Yep. Oh, that wasn't a question. So you guys have a question? Well, if you don't have a question, I will describe the minimal polynomial. Ah, wait a minute. No. Ah. Surely you guys have a question. No?
For 111A, what does it mean to show W1 and W2 are invariant subspaces of T?
Okay, so so your question is, what's the definition of invariant subspace?
Yes.
That means that when we act on the subspace, we stay in the subspace. So T of W1 is a subset of W1. Oh, you're fine. It occurred to me I was supposed to check the... Yeah, thanks. So, invariance of the subspace would mean T of W1 is a subset of W1. T of W2 is a subset of W2. That would be invariance of T. Invariance of W1 and W2 under T. Yeah. So pretty much all you got to do is look at T of, A plus BX squared and see what happens to it for W1. And you need to look at T of, AX plus BX cubed to check out W2, right? And if you get things back in the span of 1 and X squared for W1 and X and X cubed for W2, well, yeah, there you go. Invariance. But in the process of doing that calculation, you'll also discover actually what these matrices are, right? So in some sense, you can't help but do part A by doing part B and understanding it. Other questions? Yeah.
For 112, part symmetry, if you take the union of the basis for the symmetric and antisymmetric, then it would be a basis for all the matrices.
That's right.
So do you just say for the basis like E11, E12, all the way up to ENN at the basis?
No, because that wouldn't respect, when we take this union, it's not an ordinary set theoretic union. We're actually taking a union of bases. So our understanding when we take union of bases is to maintain the ordering.
Okay.
So the one you're starting to say is, I think, the lexicographic ordering, right, where we just do 1, 1, 1, 2, 1, 3, 1, 4, da, da. That's not, like the first one's symmetric, and then 1, 2 is neither symmetric nor antisymmetric, so it doesn't even belong in there. Right? In fact, a lexicographic ordered basis would not be a basis which respects this direct sum decomposition. So it's not, no, that one won't do. I can talk about how to find the basis for Sn or An if that'd be helpful. That'd be helpful? No? Yes?
So like for the symmetric ones, it would be, I think what we were thinking was it would be like Eij plus EjI or something for all of those different like possible combinations. But then you would list that
Oh,
and use
well,
it to find the block.
okay, so I think you're on the right track. So if A is symmetric, we can write it like this, right? A11, A22, ANN. Then up here we've got A12, da da dot, A1N, A23, da da dot, A2N, AN minus 1N. Okay, anyway. And then, is there anything new down here? So down here is repeats, right? In other words, if I can write it in different color, I've got A12 again here, A13 again here, A1N again here, for example, right? By the symmetry. So, you can write this, really you've got a sum, if you look at it, you've got a sum I equals 1 to n of a, I, e, I, right? And then you've also got a sum, and here's what you might not have thought of. I less than j. That's the summation you're looking at. I less than j of aij, eij plus eji. So I think that's what you're asking me is how can I understand what it is, but I don't understand how to write it down, right? So that's the first step is I mean, you can see that the diagonals and the sum of the off diagonals, right? These together span a symmetric matrix. I mean, they get an arbitrary symmetric matrix. Linear independence is easy to prove, right? So anyway, the basis, what I'm trying to say here is that the basis for this, I call it BS? Yeah, okay, so the basis for the symmetric matrix, it's got two pieces, right? It's got these EIIs, I equals 1 to n, right? And it's also got EIJ plus EJI, right? Such that 1 is less than or equal to I, which is less than j, which is less than or equal to n. I mean, that's explicitly the basis for the symmetric matrices. And then you can count, right? What does that mean? I mean, if you look at it, you can see from this already the counting. What's the number of beta s? Look at this pattern. You've got n in the top, you got n minus 1 here, you got n minus 2, 2 and 1, right? The number of the first row, everything, second row, n minus 1, and so forth and so on. So you're looking at the sum of 1 to n consecutive integers. We consult Gauss as a kindergartner, and he tells us what? N times n plus 1 over 2, right? What's the basis for the antisymmetric? So the antisymmetric matrix looks like what? zeros on the diagonal. Right, and then minus, again, the upper, the things above the diagonal are the parameters which fix the matrix, right? Because below the diagonal are automatically given to you by antisymmetry. Anyway, excuse me, beta A would be EIJ minus EJI, right? 1 less than or equal to I, less than j, less than or equal to n. By much of the same thinking. Does that make sense? I mean, again, there's some gaps in my proof. I mean, I should prove linear dependence, I suppose, or come to some, maybe there's a few gaps here, but yeah. So in the 2 by 2 case, this is just what? How big is the subspace of antisymmetric 2 by 2 matrices?
1.
Yeah, it's just 1. It's got right? Yay. But then there's 3 symmetric 2 by 2 matrices. How many things are in beta A? What's the number? Now there's where your comment could be useful, Bethany, because we could say, well, both of them together give us the basis for everything. There's n squared things in everything. So n squared minus beta sub s must be beta sub a. It's one way you could think about it, right? The number of bases in the antisymmetric should be n squared minus the number of things in the symmetric basis. Or you could just count directly, right? You could also count it. This should also be equal to what? Another way, something I think it should be the number of things in beta s, right? Another way we could look at it is number of things in beta s minus what? Yes, very good. Because we've just lost the diagonal worth of things. These will be the same thing. They both work out to n times n minus 1 over 2. All of that said, there's a way to argue this problem without actually explicitly writing either set of bases. You can just use the theory alone and well-thought arguments to avoid actually finding bases for part C.
So when it says form a basis, what does that mean?
Where does it say that?
Form basis equals.
Oh. Well, what I'm saying is you could be a little bit, in principle, you could be a little bit vague about that. You could say there exists a basis for beta A, there exists a basis for beta S of size whatever by other arguments. Or you could say there has to be, I mean, you've proved that this is an invariant subspace. You've proved that this is contained in the kernel of T, right? Which, by the way, will also give you that it's an invariant subspace because kernel T is a subset. I mean, things that are, anyway. So if you look at A and B, you've got that Sn and An are invariant subspaces, right? Which means that there exist bases for those subspaces for which the matrix is block diagonal. All right. So you could see that without even knowing their sizes. So there's kind of a vaguer solution to this. And what happens with T of A when you feed it a symmetric matrix? Well, A transpose is equal to A, right? So you get twice A for the symmetric piece. What happens when you feed T an antisymmetric matrix? 0, right? So you can kind of see what the block structure should be even without knowing those explicit bases. Because you can see what T does to a symmetric matrix, and you can see what T does to an antisymmetric matrix, even if you don't know how many explicit symmetric matrices there are and how many explicit antisymmetric matrices there are. It's a healthy thing to go through this over here because there is another class of questions I can ask which require that level of detail. So, other questions? Yes, what you said is correct. I can't say it here. I don't want to answer the question. Emma, don't pan. Right? My point is you don't actually need to know how big these blocks are to write that. Don't pan. It's okay. Oh no. Doesn't matter. I just want you guys to understand the problems. If you all find the answer and, maybe I've got some sort of stalker whose sole mission in life is to write answers to my homework questions before they're due or something. I don't know. Be an odd stalker. But anyway. Do you guys have other questions? There have been finals in the past where, like, the last problem on the final was find a basis for the symmetric, find a basis for the antisymmetric, and some questions like that. Like, I've given that as a question on the final before. More as a bonus question, though, in some previous offerings. Yeah?
This is just a general question.
Uh-oh.